Hello, everybody, and welcome to Mr. Saucedo's YouTube videos. Today, we're going to be going over a new edition of Zumdahl. So it's Zumdahl, the 10th edition. We're going to start with Chapter 4 because Chapters 1 through 3 are pretty much the same no matter what. In fact, even Chapter 4 is kind of the same in the 10th edition. But we're going to be going through specifically the non-mathematical parts of Chapter 4. So we're only covering these particular sections of the book. Eventually, we'll go back and we'll do the rest, but there are some extra bits that get added in that are extremely helpful in AP Chemistry, so just keep in mind that I'll be going through those also. So if you want to, you can kind of skip those particular sections. Okay, so section 4.1 is called Water, the Common Solvent. So there's a picture in that book that I wanted you to take a look at. And so it asks you, what are some things that you notice about this diagram? So we have an ionic compound and we have water. This is like our before picture, and this is our after picture. So what are some things that you noticed? Well, hopefully you noticed these things. So the hydrogens are blue, and they have a partial positive charge. So that's what that delta plus means. It means that it's a partial positive charge. So whereas, this ionic compound has an actual plus and minus charge, water molecules only have partial negative and partial positive charges. So for the hydrogens, they're partially positive. Hopefully you also notice that the oxygens are partially negative. They are doubly partially negative though, right? So for each, delta plus here, we actually have two delta minuses worth of charge on our oxygens. And so in the after photo here, hopefully what you've noticed is that the cations are these positively charged things. And when water dissolves something that is a cation, the water molecules are facing this particular direction. So the oxygens are touching or facing the cation because, again, opposites attract, right? So that means that this positively charged cation is going to be attracted to these negatively or partially negatively charged oxygen atoms in our water molecule, whereas the opposite is true of the anions, right? So the anions are really big in the picture here. And so you can see that a lot more clearly that the water molecules that are surrounding them have their hydrogens facing that direction. So if you've ever wondered why water is such a good solvent and why it's so good at dissolving ionic compounds, this is the particular reason why. What do we know about ionic compounds? They're made up of positive and negative charges, right? They're made up of cations and anions. And so water, because it has this partially positive, partially negative parts to itself, the hydrogens and oxygens are able to basically just kind of flip direction here and dissolve the anion by facing the hydrogens towards them, and then dissolving the cations by facing the oxygens towards them. Okay, so which of these structures do you think would dissolve in water and why? Okay, so here are two structures here. So we have this structure on the left and this structure on the right. And so I was hoping that you would choose this particular structure as being the one that would most likely dissolve in water. And from the book, it actually has this picture. So keep in mind that when we say something like dissolves like, what we're talking about are molecules that look similar to other molecules are most likely going to interact with that other molecule in a very specific kind of way. So here we have ethanol and we have a polar bond, just like these polar bonds here for water. So because these are similar, they're probably going to interact with one another, whereas water looks totally different than this structure does. Therefore, it's probably not going to interact with it at all. And so when we say like dissolves like, though, that's what we're talking about. Okay, let's go on to one last bit of this section. And so this applies what we just learned on the previous two slides. So I have A, B, C, and D. Which diagram do you think best represents potassium chloride when it's dissolved in water? So be very careful when you're looking at a particle diagram. And so hopefully you chose or selected A. Notice that the potassium cation, since it's positive, should have oxygens surrounding it, whereas the chloride ion is negative, so it should have hydrogens facing it. And so if you take a look at B and C, you can see that those are different. So be very careful when you're taking a look at a particle diagram like this. And then D is obviously wrong because K and Cl are still together, which means that it did not dissolve in water at all. And since it's ionic, since we have charged particles here, it should conceivably dissolve in water. So section 4.2, the nature of aqueous solution, strong versus weak electrolytes. This picture is directly from the book. We've got this um, green. I color coded them, right? So I said this one is our green solution, this is our purple solution, and this is our yellow solution. So what are some things that you noticed? Well, hopefully you noticed that green would be our strong electrolyte, purple would be a weak electrolyte, and then yellow would be a non-electrolyte. How can we kind of see that? Well, remember, according to this section, strong electrolytes completely ionize, meaning they turn completely into positive and negative charges. So this has nothing stuck together. All of them have been separated into positive and negative charges. Whereas for this purple one, almost all of them are still together, except for this one, which broke apart into a positively charged ion and a negatively charged ion. Notice that in this one, nothing broke apart. That means nothing ionized. That means it's a non-electrolyte. So in this section, it said, according to the book, that there are three classes of strong electrolyte. The first are soluble salts. So soluble salts are ionic compounds that dissolve in water. And so right here we have, like salt. So we have NaCl, sodium chloride. It completely breaks apart into positively charged sodium and negatively charged chloride. Strong acids are another class that they talk about. And so strong acids are things like hydrochloric acid, which 100% ionize in water. Also, we have strong bases. So strong bases are things like, again, in this item, we have sodium hydroxide. So sodium and hydroxide are completely ionized in this solution. What about weak electrolytes? According to the book, there are only two classes of weak electrolyte. We have weak acids like vinegar. And so here we can see most of the acetic acid molecules are together, except for this one, which lost a hydrogen ion and has an acetate ion left behind. Also weak bases. So a weak base would be something like NH3, that's ammonia. And ammonia is like the most common weak base that everybody uses, especially in AP chemistry, as an example of a good weak base. So notice that we have one hydroxide ion and we have one ammonium ion though, so it partially ionized. And then non-electrolytes. The book only mentions two. It mentions ethanol and it mentions sucrose. So yeah, they both have polar bonds. That means that they're going to dissolve in water, but they're not going to break apart into ions at all. So ethanol, even though it's, going to dissolve in water, it's not going to break apart into pieces. It's not going to ionize. Same thing with table sugar. So, sucrose is table sugar. And so when you put sugar in water, we know that sugar dissolves, but sugar does not break apart into ions like, salt does or something like that. So that's why this is a non-electrolyte. Okay. So let's write some equations for what would happen if the following substance is dissolved in water. So the book gives you examples of what happens when like a strong acid and a strong base, and it gives you a lot of examples of these types of equations, but I decided to go with some different ones that I thought were equally interesting and apply things that you already know from chapters 1 through 3. So magnesium chloride. So magnesium and chloride, right? They should break apart into ions because it's an ionic compound. So we should have a positively charged magnesium ion with a +2, and we should have two chloride ions. So notice that, yes, this needs to be balanced. So since we have one magnesium and two chloride ions on this side, we should have the same on this side. So yes, you do need to put a 2 in front of the chloride here. Notice aqueous is here, meaning that it is soluble. So this is an example of a soluble salt. Now take a look at this one. If you looked on our previous slide or looked at the previous slide, this looks very similar to ethanol. You don't need to know what this is called. Okay, this is methanol, but notice it says it's a liquid. So does it dissolve in water? Yeah, but it's a non-electrolyte just like ethanol is. So if you ever really see something that looks like ethanol, it's trying to tell you something. It's trying to say, okay, great, that's going to dissolve in water because it has, this polar bond that looks very similar to water, but it's not going to form any ions when it's in water. Okay, and so aqueous is still there though, because it dissolves in water. We have KOH, okay, we have potassium hydroxide. That would break apart into a potassium ion or a potassium cation and a hydroxide anion. And so again, breaking apart, this is an ionic compound. It should break apart into charged particles like that. Next up, we've got ammonium sulfate. So ammonium sulfate, we have 2 ammonium and we have 1 sulfate. Again, making sure it's balanced. Since we have 2 ammonium on this side, we should have 2 ammonium ions on that side. This should also look pretty similar to one of the ones from the previous couple of slides. It looks almost like sucrose. Again, you don't need to know what this is. I mean, you probably took biology though, right? So this is glucose. And so glucose, just like ethanol and just like sucrose, dissolves in water, but it doesn't form any ions. So again, if you see something that looks like sucrose chemically, it's probably trying to let you know that it is a non-electrolyte. HCl, hydrochloric acid, or hydrogen chloride. I guess it's hydrochloric acid because it says it's already aqueous. So HCl here would break apart into again, it's a strong acid, so that would mean it breaks apart completely into hydrogen ions and chloride ions. And then the last ones, we have aluminum nitrate. So again, keep in mind we need to have everything balanced. So this is an ionic compound. It should break apart into ions in water. We've got aluminum here with a +3, and we've got 3 nitrate ions. And then what about this one? Well, that looks again like ethanol. And so remember, ethanol, methanol, anything that has this kind of pattern to it, it's trying to let you know that it doesn't ionize, but it does dissolve in water. It's a non-electrolyte. All right, 4.5, we're skipping molarity and we're moving on to precipitation reactions. Okay, so solubility rules. Here are the solubility rules from table 4.1 in the book. Most nitrate salts are soluble. Most salts containing alkali metal ions like this, lithium, sodium, potassium, etc., and ammonium are going to be soluble. Most chloride, bromide, and iron salts are soluble, except for if you mix them with silver, lead, or mercury. Most sulfate salts are soluble with some obvious exceptions. Most hydroxides are slightly soluble, but again, soluble ones, meaning like, the ones that are always going to dissolve here are sodium hydroxide, potassium hydroxide. These ones, again, are marginally soluble. I love the fact that they use terms like slightly and marginally. Like, what does that mean if I'm asking you if it's soluble or not? The ones that you need to know, are going to be listed in a second, because one of the things that the AP exam has kind of done has gotten rid of memorizing solubility rules, which is always kind of nice. So this table will be given to you, which is kind of nice. Not on the AP exam, but on my exams. You'll be given something like this, and I'll tell you the 2 kind of rules that you actually need to memorize from it. Most sulfides, carbonates, chromates, and phosphate salts are only slightly soluble, except those containing the cations in Rule 2. All right. First question, though. We're talking about precipitation reactions. What are precipitates or precipitates? So we're talking about the noun, by the way, because it's also a verb. A solid that forms in a precipitation reaction is called a precipitate. The AP exam only has the following rules. All alkali metal salts, nitrate salts, and ammonium salts are soluble in water. So basically these 2 rules. That's all you need to know. The rest of these, you don't need to know. But I will be giving you these other rules on exams and stuff. So just keep that in mind. So let's go through. We've got zinc nitrate. I want you to write the formula and tell me, is it soluble or insoluble? So when I say that, what I mean is if it's soluble, it should be AQ. If it's insoluble, then it should be S, meaning it forms a solid. So soluble or insoluble? Soluble is AQ for aqueous, meaning it dissolves. Insoluble would be S, meaning that it forms a solid precipitate in our reaction. So zinc nitrate. Rule number 1 basically says nitrate salts are going to be soluble in water, so that should be AQ. Notice that zinc is a +2, nitrate is a -1. Cadmium sulfide. All right, CDS. So because cadmium is a +2, sulfide is a -2, that should form a solid. Sulfides are almost never going to form soluble things. They're almost always going to be insoluble. Lead 2 acetate. All right, so lead 2 acetate. Lead is Pb, by the way. Acetate, I write it this way, C2H3O2. That's the way I prefer to write acetate. And so we've got Pb with 2 acetates. If we take a look at that, it should be aqueous. Okay, again, key thing there is should be aqueous. Ammonium carbonate. All right, ammonium carbonate. We've got NH4, 2, CO3. All right, so we've got something that is definitely going to be soluble because ammonium salts are soluble. So that means it has to be AQ, regardless of what we pair it up with. Silver chloride is a great one, AgCl, that forms a solid. It's literally on the list of exceptions. It says most chlorides are soluble except for, and then it lists silver as one of those exceptions. Another one of those exceptions was lead. So lead chloride is also going to be, insoluble. Calcium phosphate, Ca3PO42, that's going to form a solid. Phosphates, sulfides, chromates, those are almost always going to be things that are insoluble for us. Lead 2 bromide, again, lead was on that list of exceptions. So most bromides are soluble in water except for lead, mercury, and silver. Barium hydroxide, okay, barium hydroxide was on our list. It says, I think it was like rule 4. It's going to be mostly soluble in water, so AQ. Sodium sulfate, Na2SO4, that's also going to dissolve in water. Remember, anything with sodium in it is going to be soluble in water. Nickel 2 hydroxide, so nickel 2 hydroxide would be NiOH2, and that's going to form a solid. Most hydroxides are going to be, soluble in water if they're paired up with something like an alkali metal or an alkaline earth metal. Most transition metal hydroxides form solids. All right. Section 4.6, describing reactions in solutions. It says, write the molecular equation for the double displacement or replacement reaction that occurs when a solution of sodium carbonate and magnesium sulfate are mixed together. So a molecular equation is what you were used to writing in your chemistry classes. So I need to know how to write sodium carbonate. So hopefully you remember that carbonate is CO3 2 minus and sodium is an Na plus. So that means the way I would write it is Na2CO3. And so since I'm mixing them together, I'm going to assume that sodium carbonate is aqueous here. What about magnesium sulfate? Sulfate is SO4 2 minus. Magnesium should be, Mg2 plus. So they already are balanced. So I don't need to have, any crisscrossing or parentheses or anything. And so that would mean it's also aqueous. So I'm going to mix these together. What would I get? Well, hopefully you remember that when we do double displacement or double replacement reactions, the cation from one pairs up with the anion from the other. And then the cation of the other one pairs up with the anion of the opposite side here. So what would I end up making? I would end up making sodium sulfate and magnesium carbonate. So that would look something like this. So why do I know this is aqueous? Well, sodium has to be. It's an alkali metal, and it's, basically rule number 2. So alkali metals are aqueous. Magnesium carbonate, on the other hand, all right, carbonates are generally speaking insoluble, so that's going to form a solid. Now, when it says a complete ionic equation, what is it talking about? Anything that's marked aqueous needs to be separated into its ions. So everything is going to get broken apart except for MgCO3, because that's a solid, that's a precipitate. So the way I would write it would be something like this. I would break apart this into 2 sodium ions, my carbonate ion, that's a magnesium ion, that's a sulfate ion. And then the opposite side, this stays together, but these guys get broken apart. All right, so what are the spectator ions from the equation we wrote in part 2? So this is our equation we wrote from part 2. Spectator ions, the way I describe them is always like, they literally are spectators. They do not actually inform the reaction. They are floating around in the solution still, but they don't actually make a precipitate or anything like that, or a gas. So if we take a look on both sides of our equation, on the reactant and the product side, there are, there are 2 sodium ions on this side and 2 sodium ions on that side. that would make them spectators. Anything that appears on both the reactant side and the product side, that's going to be an example of a spectator. The only other example of a spectator ion here are our sulfate here that we have. We have this sulfate, we have that sulfate. So everything else, this carbonate, this magnesium carbonate solid, that would be an example of what's left over. And that's what we call our net ionic equation. So this would be our net ionic equation for this particular reaction. So keep in mind, when you hear the term, molecular equation, that's what you're used to writing out. And then you have, kind of our complete equation, where now we have everything written out like this. Everything that is a strong electrolyte is going to be broken apart into pieces. Spectator ions are whatever kind of appear on both sides. And the net ionic equation is going to be this. Okay, so now let's do the exact same thing for another example here. Barium nitrate and potassium hydroxide are mixed together. Are they going to form precipitate? If yes, let's write the net ionic equation for this. So barium nitrate, hopefully again you remember, so barium's a +2. It's an alkaline earth metal on the periodic table. Nitrate is, -1, so that's how we would write barium nitrate. I'm mixing it with potassium hydroxide, right? So potassium hydroxide would be KOH. Now, it's a double displacement reaction. So barium is going to be pairing up with hydroxide. Potassium is going to be pairing up with nitrate. And the question is, do we get a precipitate or not? So barium hydroxide is soluble in water. Remember, most hydroxides are soluble in water, with the exception of, most transition metal hydroxides. And then we have KNO3. That is, again, aqueous. How do I know? Nitrates are always soluble in water, and so are alkali metals. So if everything is aqueous, that means that does not, I guess I should have actually put that down. If no, explain why precipitate doesn't form. So this reaction does not actually have a product at all. There's no precipitate here. If I mix them together, all of the ions separate. And so in reality, this doesn't really happen. So anytime you end up with aqueous, everything is aqueous on both sides, that means that pretty much all you did was you dissolved these in water. Your products that you wrote here, yeah, that's correct. We paired up our cation and anion from both parts of our reactants here, but in reality, this doesn't really happen. And so, like it says, if not, explain why. There you go. That's your reason why. So consider the following. It says, when you mix each pair together, do we get a precipitate? If so, write the precipitate down. If not, write NR for no reaction. Let's go through these. So if we mix zinc nitrate and magnesium sulfate, the zinc and the sulfate go together, the magnesium and the nitrate go together, and so nothing happens. Zinc sulfate is soluble in water, magnesium nitrate is going to be soluble in water. Okay. Next, we've got silver nitrate, potassium carbonate. Yes, we have a precipitate. So silver is going to pair up with carbonate, potassium is going to pair up with nitrate. Potassium nitrate is soluble in water. Silver carbonate, though, is not. Most carbonates are not. And silver is one of those, rare ions where anytime you see silver, it's probably going to form a precipitate. Next, we have calcium hydroxide and copper 2 chloride. So that's going to make calcium chloride and copper 2 hydroxide. So do we have a precipitate? Yes, we do. We have hydroxide with a transition metal. So that's going to be our, precipitate. Whereas calcium chloride is definitely going to be soluble in water. Next, we've got lithium sulfate and barium bromide. So the lithium is going to pair up with the bromide. The barium is going to pair up with the sulfate. Lithium bromide is definitely soluble in water. Barium sulfate, though, is not. So barium sulfate is going to form a solid precipitate. Sodium acetate, potassium phosphate. So that means the sodium is going to pair up with the phosphate. Potassium is going to pair up with the acetate. Do we have a reaction there? No, we do not. Lead 2 nitrate and sodium bromide. So lead 2 gets paired up with bromide. Sodium gets paired up with nitrate. So sodium nitrate we know is going to be soluble. Lead 2 though, bromide, anytime we see lead should let us know that, great, we're going to have something solid forming. Next, we've got sodium chloride, or sorry, I guess I should continue with the pattern I was using before. So we have sodium phosphate plus nickel 2 chloride. Sodium is going to pair up with chloride. That's salt. Obviously, that's soluble in water. Nickel 2 phosphate, though, that's going to be something that's definitely a solid. So again, that would be how I would go very quickly through, do we have a reaction happening here or do we not have a reaction happening here? Now, it does ask us then to write the reactions for them. So I'm not going to bore you with how to do the net ionic equations for all of these. But again, if you go back, this is how I would make my silver carbonate. This is how I would make my copper 2 hydroxide. This is how I would make barium sulfate. This is how I would make lead 2 bromide. And this is how I would make nickel 3 phosphate. Again, go through, write your net ionic equations for these particular reactions. And it's easy if you write the whole molecular equation, then you write the complete one, and then you start crossing out spectator ions until you get to this point. Or you can do the shortcut kind of way. If you've kind of noticed patterns that are always kind of popping up when writing them. All right, next, section 4.8, acid-base reactions. So acids are substances that do what? According to the book, they produce H plus ions when dissolved in water. Bases are substances that produce OH minus ions when dissolved in water. Now, that is the Arrhenius definition, which we'll talk about eventually in second semester. There is a better, more general definition, which we're also going to talk about next semester, and that is that acids are proton donors, bases are proton acceptors. So this is what we mean when we say proton donor and proton acceptor. Right here, this H is going to get donated to the H2O, making an H3O plus. Now notice when this H is gone, now this overall ion has a negative charge to it. Okay, so important stuff that's not in the actual chapter, but you need to know. This is the majority of the last part of this video. So if you need to skip this part, it's in the description. So you can just skip to the next actual section from the book. But this is super important stuff. So I thought it would be useful for us to go through it now. So what is a monoprotic acid? So a monoprotic acid is an acid that only donates a single proton. It asked you to find 2 examples. And so here are just 2 examples that I found. There are plenty though, right? Hydrochloric acid, nitric acid. You could have done perchloric acid or chloric acid or nitrous acid or, anything really here. And so monoprotic acid has a single H though in it. Oh, acetic acid would be another good one. What about a diprotic acid? So mono means 1, di means 2. That's an acid that can donate 2 protons per molecule of acid. And so it said to find 1 example. I'm just going to give you 2. Carbonic acid, which you find in like soft drinks and sodas, and sulfuric acid, which sometimes happens in acid rain. But notice that you have 2 H's here. That's diprotic. Now, acids can be described as either strong or weak. I figured it would be important, since we're talking about electrolytes, for you to know what strong acids are and what the 7 strong acids that you need to memorize are. So strong acids 100% ionize in solution, whereas weak acids partially ionize, like 5% or less. I normally think it's about 1% of them ionize. But what are the 7 strong acids? So again, circle them is what it says. That's a strong acid. That's a strong acid. That's a strong acid. Am I missing one? Yeah. 1, 2, 3, 4, 5, 6, 7. That means everything else here, all the rest of these, must be weak acids. All right, let's write down the names and stuff, though, and formulas for them. So HClO4 is perchloric acid. HClO3 is chloric acid. HCl is hydrochloric. HBr is hydrobromic. HI is hydroiodic acid. And then we've got nitric acid. And then the only diprotic strong acid that we have on here is sulfuric acid. It's the only one on the list. So know these 7 strong acids. They will be your friends. I mean, you know what I mean when I say something like that. Strong bases. All right, so what about strong bases? Weak bases only partially ionize. Here are our strong bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. That's every alkali hydroxide. So every first group on the periodic table with an OH after it. I did not put francium hydroxide because it doesn't really exist, but technically that would also be a strong acid. And then there are 3 alkaline earth metal hydroxides: calcium hydroxide, barium hydroxide, and strontium hydroxide. Those are also strong. Okay. They sometimes call them, by the way, the heavy alkaline earth hydroxides. All right. So again, what about weak bases? So weak bases are things like ammonia, NH3. And so anytime you see NH3, just know that it's probably trying to let you know it's a weak base. But another good example of weak bases are amines. Now, amines are derived from ammonia. So remember, NH3 is what we're talking about when we say ammonia. And so instead of hydrogens surrounding our nitrogen here, at least one of them has been replaced with a carbon atom, okay? And so when amines react with water, that lone pair of electrons from the nitrogen atom is able to bond with a hydrogen atom from the water, giving us a positively charged cation and making a hydroxide ion. And remember, hydroxide ion formation is one of the things that lets us know that we have a base. So when it says write an equation for what happens here, it's going to look kind of weird and a little messy, but again, it'll make sense when I show you a picture of what's happening at the molecular level. So methylamine is just this: CH3NH2. We have water. One of the H's from the water here is going to move and attach itself to methylamine. When it does that, now instead of NH2, we have NH3. And that forms a positively charged thing. And now what's left over? Well, if I remove an H from water, I end up with OH minus. So here's what's actually happening. And notice ammonia is NH3. So this is very similar. We have, 2 H's here, and then we have a CH3. So this kind of bond would have been an H for ammonia, but instead it's been replaced with a CH3, a methyl group. And so this pair of electrons is going to basically attract this H, and this H is going to now form a bond here, making this a positively charged ion. And what's left is we have an OH minus group here. So now we have hydroxide. And that's what happens with weak bases. So this entire thing here, that's our reaction for a weak base. Notice that there is a double arrow. The double arrow lets us know that in reality, this is weak. This is not a strong thing that's happening. This is a weak thing that's happening. So next, dimethylamine, same exact thing. Notice that now we're basically, removing an H from water. And as a result of that, we're gaining an H here. And so by gaining an H, this becomes positive and we're left with an OH minus. Exact same reaction, but now instead of a single, instead of 2 H's, now we have 2 CH3 groups. And you can imagine that there's a trimethylamine where we have 3. All right. So using the information we collected, let's see if we can figure out what's going on with this chart. So is a substance soluble in water or not, right? That's what we really care about. It says a certain substance is soluble in water. Great. So it's soluble. Is it ionic or covalent? Well, if it's ionic, what do we know? Is it strong, weak, or a non-electrolyte? Answer: if you see an ionic substance, we're going to say that's a strong electrolyte. Okay, assuming it's soluble in water. That's why the solubility rules are so important. Okay, next, what if it's covalent? Well, then we have to ask ourselves, does it have acid or basic properties? If the answer to that is yes, we have to ask ourselves, is it strong, weak, or not an acid or a base? So is it a strong acid? If the answer to that is yes, it's a strong electrolyte. Now you might ask yourself, why doesn't it say strong bases? Strong bases are all ionic by nature because they have a cation and an anion. So strong acids are really the odd one out because they can technically be covalent, like, HCl. Those are both nonmetals. So that's why this is kind of separated, and you're like, where are the strong bases? They're right here. Okay, so strong bases are included in, ionic substances here. Weak acid or weak bases. Well, if we have a weak acid or weak base, it's a weak electrolyte. And then if it's not an acid or a base, if it's covalent, but it's not an acid or a base, then that means it's not an electrolyte. That would be things like we saw previously: ethanol, methanol, sucrose, glucose. Okay, so let's classify the following. Strong, weak, or non-electrolyte. All right, so I'll tell you what I would do first. The first thing I would do is which are ionic compounds that are soluble in water. Let's see if we can find them. All right, first one I saw right here, KNO3, potassium nitrate. Cross it off our list. Next one I see, all right, I see sodium acetate. Okay, so sodium acetate's right here. That's going to be soluble in water. Next, barium hydroxide. Again, ionic. So it's an ionic compound, soluble in water. Which are our strong acids? HBr, hydrobromic acid. I don't see any other strong acids here. Now we have to ask ourselves, what about weak acids? All right, how do I identify weak acids? Well, HNO2, that's nitrous acid. You know, it looks like it could be nitric acid, but it's not. It's nitrous acid. It's missing an O. So that means that that must be a weak acid. Remember, acids, generally speaking, start with an H. I tend to not write acetic acid like this. I like putting the H at the beginning just to like let everybody know that it's, a weak acid that we're looking at here. The way it's written here is to show that it has an OH here, meaning that it has a polar bond. So some people like writing it this way, but this is vinegar. Okay. Which of these are weak bases? Well, I see NH3, so that's always easy to identify. And then do we see any other ones? Oh yeah, I see an amine right there. What about these last ones? Glycerol, glucose. Look how similar those look. Those are both non-electrolytes. And then take a look at this. We have ethanol, and this is an ether, but it looks very similar. So the last four have to be non-electrolytes. Again, notice how similar the non-electrolytes are to each other. That's kind of the key. Okay. So now we want to be able to write different types of acid-base reactions. We want to write their molecular equation, their complete ionic equation, their net ionic equation. It says ignore S, L, G, or AQ for these type of ones just because it would get a little confusing, and we're not trying to confuse you. So what happens if I have a strong acid and a strong base, like hydrochloric acid and sodium hydroxide? So molecular equation, I need to know hydrochloric acid is HCl, sodium hydroxide is NaOH. What am I going to get? Double displacement, really, right? So the Na and the Cl are going to hook together, and we're going to get sodium chloride. The H and the OH are going to go together, and I'm going to make, a lot of times people say hydrogen hydroxide. Well, what is HOH? It's water, H2O. Everybody always says, oh, yeah, okay. Because literally, when you put an H and an OH together, you now have H2O. So what's the complete ionic equation? Okay, well, these are strong. They have to be soluble, right? They have to be aqueous, so I should be able to separate them. NaCl also is going to dissolve, so I have to be able to separate all that too. The only one that wouldn't would be this covalent compound water because, is water soluble in water? I mean, I guess technically it is. It's like asking, is water wet? But H2O would stick together. It's covalent. Okay, so what are our spectators? Cross them out. And I'm left with H plus OH minus gives me H2O. Let's try another one. Nitric acid and calcium hydroxide. Okay, what's nitric acid? HNO3. What's calcium hydroxide? CaOH2. Okay. HOH, water, calcium nitrate. Okay, so H2O, calcium nitrate. Keep in mind this isn't balanced, right? Like it's bothering me already that it's not balanced. So let's balance it. So I put a 2 here because I have 2 nitrates. Now I have 2 hydrogens, so that must mean I have to put a 2 in front of the water, and now I have a balanced equation. All right, these are both strong. They should break apart completely. This is ionic. It should break apart. So I should end up with something that looks like this. What are my spectator ions? I can cross out the nitrate and I can cross out the calcium. And now I'm left with HOH gives me H2O. A lot of times people say, can I put the 2 in front of it? It's supposed to be reduced to its lowest number. So technically, I'd want to reduce this to just H plus OH minus gives me H2O. But notice that for strong acids and strong bases, the net ionic equation is always making water. Okay. Weak acid, strong base. Okay, acetic acid. Acetic acid can be written many ways. Again, I'm going to write it this way simply because a lot of times in the book, they like writing acetic acid this way. I still like just putting HC2H3O2, but that's just me. And then we have KOH, that's potassium hydroxide. Okay, so what's going on here? I guess, this kind of makes sense then. So this H and this OH are going to come together here, H and OH, to make water. This K is going to basically replace the H. And so now I'm going to get potassium acetate. So again, water, potassium acetate. So is this a strong electrolyte? It is not. Is this a strong electrolyte? It is. That's why it has the word strong here, right? And this is ionic, so it has to break apart. Okay, so my acetic acid is going to stick together. My water is going to stick together. And then notice the K is the only spectator ion for this. And so I have acetic acid plus hydroxide gives me water and an acetate ion here. Okay. So next, nitrous acid, barium hydroxide. All right, again, I've got my weak acid and my strong base here. So nitrous acid is HNO2. Barium hydroxide is BaOH2, remember? So I'm going to have an H and an OH to make water. Barium and nitrite are going to get together to make barium nitrate. Is it balanced? Nope, not balanced. Let's balance it first. Complete ionic equation. Okay, this is weak. It's not going to break apart. This is a strong electrolyte. It is going to break apart. This is ionic. It's going to break apart. So really, the only two things that break apart are my barium nitrate, my barium hydroxide. So what do I have spectator ions of? It looks like it's just the barium. And so now I'm left with something that looks like this. Again, we want to lower it. We want to reduce it. So I'm not going to have twos in front of everything. I'm just going to reduce it to its lowest common number here. All right. Now, strong acid, weak base, hydrobromic acid, ammonia. Okay, HBr is hydrobromic acid, ammonia is NH3. It's going to make ammonium bromide. Okay, so, and again, kind of think about this. So this H is going to go here to make NH4. And remember, NH4 is a plus, so it's NH4 plus. What's going to be left over is Br minus. They're going to basically hook together and make ammonium bromide. So let's separate our strong and our ionic. And now Br is pretty much the only thing that I have in common here. So this would be my net ionic equation for the manufacturing of ammonium. Chloric acid and methylamine. All right, chloric acid is HClO3. That's a strong acid. Methylamine, weak. Okay, this H, remember, is going to go here to make this a positively charged cation, and I'm going to be left with a chlorate ion then. And so if this is positively charged and my chlorate ion is negatively charged, they're going to basically hook together and make this compound. Okay, so this is strong. This is now ionic. It's going to, kind of break apart. And so this is weak. It stays together. Okay, chloride ion goes away. And now I'm left with just this. Again, notice the patterns, right? So for a strong acid and a weak base, this is the pattern. Okay. Weak acid, weak base, hydrofluoric and ammonia. All right, HF and H3. A lot of times people think hydrofluoric acid is a strong acid, but it's not on our list of strong acids, so it's not. Okay, can you predict what's going to happen? Well, the H is going to move from here to here. That's going to make ammonium. Fluoride is going to be left over, and and that has a negative charge. So now they're going to hook together to make ammonium fluoride. And so this is ionic. This is not. Look at the net ionic equation. They're the same. So for weak acids and bases, your complete ionic equation, net ionic equation are the same because nothing can break apart, right? Like literally, that's it. These are both weak. We can't cross anything out then. So last but certainly not least, certain anions can react with acid to produce gases. We call these gas-forming reactions, but they're still really acid-base reactions. So anytime you see sulfides, okay, like, pick a cation, pair it up with sulfide, you can end up making a particular type of gas. And so that would be hydrogen sulfide gas. So a lot of times when you see sulfides mixed with acid, just know you're going to produce H2S gas in your reaction. Carbonate and bicarbonate ions, when you mix them together with acid, they produce CO2. Sulfide ions, when mixed with acid, will end up producing SO2. Now, keep in mind, like, this is why vinegar and baking soda end up making bubbles of CO2, because, again, vinegar is an acid. Baking soda is sodium bicarbonate. So that's why we end up making CO2. Okay. So let's see if we can figure out how to do this for a gas-forming reaction. Sodium carbonate, hydrochloric acid. Again, I have a carbonate and I have an acid. That means that I'm going to be forming something like CO2. So sodium carbonate, Na2CO3, hydrochloric acid, HCl. So the way I always like to think about it is I remove CO2 from this now. So boop, CO2 goes here. I have an H, and I basically have an O. All right. Now that means I'm going to be making water from those. And then I'm left with Na and Cl, so that's going to make salt. So the Na and the Cl pair up, right? That's kind of easy to picture in our heads. The H and an O is going to pair up, and then CO2 is left over. Now, why isn't this just, OH minus or something, right? Well, it can't be because we're mixing a strong acid here. So there's going to be a lot of H's. That means that we're going to end up with H2O. And so if I'm going to balance this, I would put a 2 there, and I would put a 2 here. So that's also another reason why we don't just end up with OH minus or something. We end up with H2O. And so what's the complete ionic equation? So we want to separate strong things and ionic things from each other. So this is ionic, this is strong. CO2 cannot get broken apart, it is covalent. H2O cannot get broken apart like that either, it's covalent. So what are our spectator ions? This would be our our net ionic equation for sodium carbonate and hydrochloric acid. All right, now, last section. 4.9, oxidation reduction reactions. So this is the table directly from the book, 4.2, rules on assigning oxidation states. So here are our general rules for assigning oxidation states to various things. Keep in mind that oxidation numbers, which is what we're technically talking about here, are just ways to keep track of electron movement in redox reactions. So a lot of times it's like a accounting measure to just make sure we know what we're talking about. It's not reality. So in reality, fluorine here in PF3 does not have, a -1, because we already know that this is a covalent compound. So it's sometimes just a nice way of keeping track of what electrons are doing, though, which is why we use this particular type of method to track electron movement. And so, like it says, picturing the charges lets us know which direction electrons are moving, which can be useful to us. So we're going to basically use these rules. An atom in an element has an oxidation state of 0. Monatomic ions should have the same charge. So we know Na plus, we know sodium in an ionic compound always has a +1. We know chloride in a ionic compound always has a -1. Fluorine has a -1, no matter what. Oxygen has a -2, with an exception of in peroxides, it has a -1. Hydrogen has a +1 in covalent compounds. Okay, so what we're going to do is we're going to use our oxidation state rules list in order to figure out what the oxidation number or the oxidation state of each one of these elements is. And some of them are standalone, some of them are ions, some of them are polyatomic ions, and then some of them are just, regular molecules or ionic compounds. Okay, so rule number 1, an atom in an element is 0. Okay, so that means iron by itself should be 0, zinc by itself should be 0, oxygen should be 0. Okay, that's O2, by the way. This second rule says a monatomic ion is the same as its charge. So an aluminum ion should be a +3 oxidation number. Sulfide ion should be a -2. Barium should be a 2+ or +2. Okay, now everything that follows is pretty much going to include either fluorine or oxygen or hydrogen. If they don't include that, then that must mean that it's probably ionic, and we're going to have to use this monatomic ion rule, using the periodic table, +1, +2, +3, etc. Okay, so H2O, we go in order going down. So like this is our first rule, second, third, etc. So there's no fluorine. Oxygen's the very first one that comes up, right? So O should be a -2. And if O is a -2, each hydrogen, since I have two of them, has to have a +1 because this is a neutral molecule. So that means it would take two of these and one of these in order to add up to 0. H2O2, that is a peroxide. So since it's a peroxide, it says oxygen has a -1 oxidation number. And so since it has a -1 and there are two of them, that means that adds up to -2. So that means that hydrogen has to have a +1. Again, right? Two of these add up to 0. Okay. OF2. So fluorine is a -1 in all of its compounds, so it has to be -1. And so if we have, OF2, that means oxygen would have to be a +2 because it takes one of these and two of these in order to balance it and make it neutral. Okay, here's a weird one. So hydrogen is a +1 in its covalent compounds. This is not a covalent compound. How do I know that? I have sodium, which is a metal, hydrogen, non-metal, so it can't be. Okay, so that means I should go with what charge should sodium have in a ionic compound? Should have +1. That means hydrogen must have a -1 in this one. Also, this is a hydride ion, and hydride has a -1 charge, so you could have also used that logic. CH4, again, hydrogen has a +1 in its covalent compounds. So if this has a +1, carbon must have a -4 to balance that out. So, because it takes 4 of these and 1 of these in order to balance it. Next, again, we have oxygen, so that's a -2. That means that this carbon has to have a +4 in order to get it to be balanced because it takes 2 of these and 1 of these in order to add up to 0. Now, the next couple, in fact, the next 7 or 8 of them, are polyatomic ions. So for all of these, they had to be adding up to 0 when we were doing our oxidation number allocation. Here, they have to add up to the number that is the charge of this ion. So everything that I add together has to add up to -1, -1, -1, -2, -2, -2, -3, -1, +1. So anytime I see a polyatomic ion, that means that I have to be aware that all of the stuff that I add together has to add up to the overall charge of this particular polyatomic ion. So again, oxygen's the first rule that we hit. So that means oxygen's a -2. What must hydrogen be? A +1, because -2 + 1 is -1. All right, next. Oxygen is a -2. I have 3 of them. That's a -6. What must chlorine be in order to add up to -1? It has to have a +5. Same thing here. -2 times 3, that would be, again, -6. I have to have this be a +5 in order for it to add up to -1 for nitrate. Next, I have carbonate. -2 times that. That means I have -6. That means carbon has to have a +4. Next again, I have another one with oxygen in it. So -2 times 4 is -8. That must mean this is a +6 for my chromium in order to add up to -2. All right, next, again, -2. Carbon has to have a +3 in order to get this to add up to -2. Next, we have phosphate. Again, -2 times 4 is -8. That means that this phosphorus has to have a +5 in order to add up to -3. All right, same thing, -2. That's, again, times 3 is -6. Hydrogen has to have a +1 because it's a covalent compound. That means that whatever's left over has to be the charge of carbon, which is a +4, to get us to a negative value. So that's what bicarbonate's oxidation state numbers would look like. Last is ammonium here for our, 8 charges in a row or something like that. So hydrogen has to have a +1. That means that nitrogen has to have a -3 in order to have this add up to a +1 charge. Okay, we have N2H4. Hydrogen has a +1. Nitrogen has a -2 then in order to add up to 0. Again, all of these ones that we just did from hydroxide all the way to ammonium were polyatomic ions. These ones right here, these two are not. Okay, oxygen again has to have a -2. Hydrogen has to have a +1 because it's, again, another covalent looking compound here. We don't see any metals. So that means that nitrogen would have to be a -1 in order to get this to work out. All right, next is nitrite, and then we have nitrate. So again, another -2. Nitrogen would be a +3 in order to get this to add up to a -1 charge. Next, we have again another -2 for oxygen, +5 for nitrogen in order to get to a -1 charge for nitrate. Hydrogen's a +1, that means chlorine's a -1. Again, as we go through these, you probably will start to see all of the patterns. So -2, +1, +7. -2, +1, carbon would have to be a -2 in ethanol then. And then we've got -2, +1, that means sulfur is going to be a +4. And then in sulfuric acid, we've got -2, +1, that means sulfur would be a +6. So again, these rules are super easy to kind of just remember when you're doing so many examples of them. So for, plain old atoms, it's easy. For monatomic ions, it's super easy. And then for most common compounds, it's pretty easy also. Like, look how frequently oxygen appeared and what its, oxidation number was. There was one exception here where oxygen did not have a -2. Same thing with hydrogens. Hydrogens are all over the place, and almost always they're a +1. You can look through plenty of examples, and again, there's like one example where it's not a +1. And fluorine's always a -1. That's the only one that doesn't have any exceptions here. So again, using those three, we can pretty much figure out the oxidation state or number of anything. So what is oxidation? Great, we learned how to assign oxidation numbers. What is oxidation? Oxidation is an increase in oxidation state. Reduction is a decrease in oxidation state. I always think that's kind of easy to remember because when we hear reduction, we think decrease or reduce, right? Oxidation, though, means an increase. So what does that mean when we're talking about, reactions? So when an element loses an electron, it becomes oxidized. When an atom gains electrons, it becomes reduced. And so the two pictures that everybody always uses is Leo says Gur and oil rig. Oil rig, oxidation is loss of electrons. And when you lose electrons, you increase your oxidation state. Reduction is a gain of electrons. When you gain electrons, you decrease your oxidation state because electrons are negative. Okay? So lose electrons, oxidation, gain electrons, reduction. That's, again, just kind of like our common ways of remembering these types of things. So let's pretend we have calcium reacting with oxygen to form calcium oxide. So I have Ca plus O2 gives me CaO. Which element is being oxidized in this reaction, which is being reduced? Okay, so remember our oxidation number rules. Calcium, pure element, 0. Oxygen, pure element, 0. What is calcium's charge? +2. What is oxygen's? -2. And I guess I should have done the oxygen one first, because remember our rule says oxygen's a -2 unless it's in a peroxide. So I'm going from 0 to +2. I'm going from 0 to -2. So for calcium, I'm going from 0 to +2. Oxygen, I'm going from 0 to -2. Which one's being oxidized then? Calcium's going from 0 to 2. Therefore, it is being oxidized. Its oxidation state is increasing. Which element is being reduced? Oxygen's is going from 0 to -2. Its oxidation state is decreasing. It's going down. So that's how you identify which element is oxidized and which is reduced. And we can do this for any reaction. So sodium reacting with chlorine to form sodium chloride. Sodium, pure element. Chlorine, pure element. Salt, not, right? It's an ionic compound. So 0, 0. I don't have anything from the rule here, but we know this is charged. So that means that sodium has a +1 because that's what our charge is for sodium on an ionic compound. That means that chlorine must be a -1. And so again, we have to think to ourselves, sodium is going from 0 to +1. Chlorine is going from 0 to -1. Which one's oxidized? Sodium. It's increasing 0 to 1. Chlorine decreasing 0 to -1. So it's getting reduced. All right, let's do more here. In the reaction above, magnesium is oxidized or reduced. So we're going to circle one. It's going from what charge to what charge. Hydrogen is being oxidized or reduced. It's going from what charge to what charge. All right, let's go through this. Magnesium, 0. Here I have hydrogen, +1. Chlorine must be a -1 then. On the opposite side, I've got, again, chlorine -1. Magnesium is +2. Again, I know magnesium has to be a +2. Chlorine has to be -1. Good old ionic compound rules. Hydrogen is neutral, so it's 0. It's a pure element. So which one is magnesium? It's going from 0 to +2. That means it is being oxidized because it's going from 0 to +2. Hydrogen, on the other hand, is going from +1 to 0. It is getting reduced. It is literally decreasing its oxidation state, going from 1 to 0. Next, the above, sulfur being oxidized or reduced. What about the oxygen? Okay, so sulfide, -2. That means that our lead must be a +2. This is hydrogen peroxide. Remember, oxygen is a -2, but in a peroxide, it's a -1. Hydrogen must be a +1 then in order to balance that out. Next, we've got, again, oxygen, -2. Lead is a +2. In fact, we found that over here. What must the sulfur be then? It has to be +6. And then we can finish up with just water, -2, and then +1. Okay, so let's take a look at sulfur. -2 to +6. It's being oxidized, increasing by a lot, by 8 electrons. Oxygen, on the other hand, is being reduced because it is going from -1 to -2. That's a reduction, even though it's just, it's just 1 electron difference here. Yeah, that's still technically a reduction. Next, we've got iron 2 sulfide, nitric acid. All right. So sulfide is in -2. That means that this must be a +2. Again, it's ionic, so kind of easy to figure that one out. Here, okay, let's use our rules. -2 for oxygen, that's -6. Hydrogen has a +1. That means this nitrogen is a +5. Okay, iron here. Oh, well, let's do nitrate again. Nitrate didn't change, though, so I always say, just it's the same thing. Iron here, +2. Hydrogen and sulfur again, we've got a -2 and a +1. Is the reaction above a redox equation? If so, why? If not, why not? None of the numbers changed. Iron's a +2, it's a +2. Sulfur or sulfide, -2, -2. So nothing changed. This is not an example of a redox reaction. So just assigning oxidation numbers to something, right? You can tell whether this means this reaction is redox or not. Okay. For each of the following reactions, determine if any elements are being oxidized or reduced. If there is an oxidation reduction, identify the oxidation numbers for the elements that are changing on both sides. So we're going to do the exact same thing we did, and I'm going to go kind of quick. So we know that's a +1. Means that has to be a -3 to give us our ammonium, and that means that must be a -1 because we know chloride is a -1. Okay, -2, +1. That means that's a +1. Again, charges, we just kind of know that. Same thing with this. We kind of know what the charges of these are. Hydrogen's a +1. Remember, in covalent compounds, that means that's a -3. Again, -2, +1. So taking a look at these, are any of the oxidation numbers changing? They are not. That means it's not a redox reaction. All right, next, 0. -2, +1, +5. Okay, next, -2, +5, because we have nitrate, so it's the same. That means that our copper here is a +2, which I guess I could have also gotten by reversing the crisscross, but you get the idea. Silver, 0. Copper is going from 0 to +2. It's being oxidized, right? 0 all the way to +2. That means silver is being reduced. It's going from +1 to 0. A lot of times people ask, can we just have oxidation or can we just have reduction? No. In order for something to be oxidized, something has to be reduced. You can't have one without the other. There's no such thing as just oxidation or just reduction. Okay. Cl2, we know that's 0. It's pure. It's 1 for potassium, -1 for bromide. Again, know that. That's 0. So yes, we do have a change here. Bromine is going from a -1 to a 0, so it's getting oxidized. Chlorine is going from 0 to -1. It's reduced. What about this one? All right. Negative 2 times 3, that's a plus 2. That means this has to be a plus 4. Negative 2 plus 1, that means sulfur has to be a plus 6. Again, negative 2, that's a plus 2. That's still a plus 6. Negative 2 plus 1, negative 2 plus 4. Nope, not a redox reaction. All that work just to say, no electrons are being transferred. So nothing's being oxidized or reduced. All right. Write the net ionic equation for the following. All right, so it's the exact same as before. There are no special rules here. So remember, if I have a strong acid, that means it's a strong electrolyte. That's going to break apart completely. This is aqueous, and it's a soluble salt, so it's going to break apart completely. So when I'm writing a net ionic equation, this would be our complete ionic equation. Cross out your spectator ions, and then whatever is left, that would be our net ionic equation. Notice that I had to keep the 2, 6, 2, and 3 because each one of these is that lowest possible number that I could get balancing that particular equation. All right, next I've got iron, nickel 2 nitrate, making iron 2 nitrate and nickel. So again, if I were to break these apart, those are soluble salts. These are soluble salts. I can break them apart. And so I end up with something that looks like this. That would be my overall net ionic equation for that particular reaction. Important but not in the chapter. Okay, so this is like the last bit. Standard reduction potential. So if you look at the back of your book, there is an appendix called 5.5, and it has this, which looks really confusing. Again, redox is really electrochemistry, so we're going to be looking at it eventually again, but I felt compelled to tell you this information now. So what is this? How do we interpret this, and what is this showing us? So metals at the bottom of the table with negative values. So we have lithium, we have potassium, barium, calcium, sodium, lanthanum, etc. And we go, kind of up this way. So the more negative the potential is, the more easily oxidized these are. So lithium is the most oxidizable element on the periodic table. The metals near the top here and nonmetals, okay, have positive potential. So fluorine right here are extremely stable. And so these are the most easily oxidized things. And yes, it continues. So in case you're wondering, it goes up and then it stops. It goes back here at the bottom and then it goes up. So these must be the most easily reduced. So easily oxidized are here, easily reduced are here. And again, it does travel up. So they kind of meet in the middle, and hydrogen is perfectly zero in between both. So how can we use that reduction potential table in order to answer some questions about redox reactions? So again, I felt compelled to kind of connect both of these things together. So not every redox reaction is possible. And what I mean by that is there is a list, and it was on the previous slide right here, of easily oxidizable and easily reduced materials. Now, the rule is that any metal with a more negative potential, so these guys, can be oxidized by an element below it. But that doesn't go the opposite direction. So that means that you cannot have something with a more negative potential being reduced. And so for this example here, it says we have tin and we're mixing it with magnesium nitrate. We want to determine, does a reaction occur? And if it does occur, write the net ionic equation for it. Okay, so let's just write a bare bones molecular equation for it. Tin is SN. Magnesium nitrate is MgNO3 2. And so this is a single displacement reaction. Tin is going to try to push magnesium out of the way. So if this reaction worked, I would end up with tin 2 nitrate, and I would end with magnesium. A lot of times people ask, how did you know that this tin was going to be like a +2 and not like a +4 or something else? You don't. Generally speaking, though, if a particular transition metal is replacing another non-transition metal, like magnesium has a +2, it's going to have the same charge. So it doesn't really matter whether you picked tin 2 or tin 4, but we have to basically figure out still oxidation numbers. So tin is 0 here, whereas here it's a +2. Magnesium is a +2, here it's a 0. I'm not even going to find the oxidation numbers for the other things because all we care about are the things that are changing. And so here I have, a metal replacing another. And so here's the important part. Which one's being oxidized and which one's being reduced? Can tin be oxidized and magnesium be reduced? So tin is being oxidized because it's going from 0 to +2. Magnesium is +2 to 0. Is this allowed? Well, we have to look at our list. So let's find magnesium and let's find tin. That's magnesium, negative 2.37. That's tin, and notice it's tin too, negative 0.14. So remember, things here are more easily oxidized. Things down there were more easily reduced. Magnesium should be the one that is being oxidized, and here it's being reduced. That means that this is not going to happen. So again, whatever is being oxidized needs to appear more negative or needs to appear less positive than whatever is being reduced. That's the only way for the reaction to actually work. So this, would never happen. All right. Aluminum metal is added to copper 2 chloride. So we know aluminum's Al, copper 2 chloride is CuCl2. So what's happening? Aluminum is going to try to replace our copper here. And so we're going to end up with aluminum chloride. And notice, aluminum always has a +3. So it couldn't replace something exactly. Copper is going to be just by itself. So again, aluminum goes from being 0 to having a +3. Copper goes from having a +2 to having a 0. So the question we have to ask ourselves is, can aluminum be oxidized and can copper be reduced? So aluminum is going from 0 to +3. It's increasing its state. That means that it is being oxidized. +2 to 0, it's being reduced. Okay, so let's take a look at our chart. Where's aluminum and where's copper? So aluminum is right here, negative 1.66. Copper, and notice it's copper 2 plus, is 0.34. Can aluminum be oxidized? Yes, it can. It's more negative. Copper can be reduced. It's less negative. In fact, it's more positive, right? So yes, this can happen. This is a totally acceptable reaction. This could definitely happen. Zinc being added to hydrobromic acid. So zinc plus hydrobromic acid. And if you're wondering why I'm not writing HBr, it's because I don't care about the Br. The Br is a spectator ion. And if you don't believe me, you can write it out yourself. Okay. What do we get though? I'm going to be making zinc bromide. So zinc goes to being a 2 plus, and hydrobromic acid, right? So I'm just going to have hydrogen gas being manufactured. And again, if you don't believe me, feel free to write it out yourself. So zinc goes from a 0 to +2. Hydrobromic acid goes from a +1 hydrogen to a 0. So the question is, can zinc be oxidized and can hydrogen be reduced? So I need to find zinc right here, and hydrogen's right here at 0. Zinc is more negative. So that means this can definitely happen. If I put zinc in acid, I'm going to end up getting bubbles of hydrogen gas. And so, yes, this can happen. Zinc is oxidized more easily than hydrogen. And notice hydrogen is 0. These are called standard reduction potentials because they use hydrogen as the 0 point for calculating this particular table. Next, gold metal is added to a solution of hydrochloric acid. So I have gold. I have, again, hydrochloric acid. I don't care about the chloride because it's a spectator ion. Gold forms a +3 ion frequently, and on our chart, it has it as a +3, so I'm making it a +3. So it would be making gold 3 chloride and H2. Does it matter though? Like, what if you said gold 2? Okay, like that's totally fine. Okay, so 0 to +3, +1 to 0. Can gold be oxidized and can hydrogen be reduced? Well, I actually need both parts of the chart for this because hydrogen 0, gold is 1.50. It really doesn't want to be oxidized. like really doesn't want to be oxidized. So this is also impossible. That's the reason why, gold doesn't dissolve in a single strong acid. In fact, you need something called aquaregia in order to get it to work. Okay, so that's it for this first part of Chapter 4 for Zumdahl, the 10th edition. If you have any questions, please leave a comment. I'll do my best to answer it. And it takes a while to go through these. So it might be a while before part 2 comes out. But still, if you have any questions, please let me know. And I'll try to get back to you. Thanks again for liking and subscribing.